Alright, before we get too much farther in, we should probably define what we mean by a few terms. So, um, what is a radial function? A radial function is any function of the form. I'm going to use phi just because it's kind of a classic, but we could use f, I suppose. F doesn't depend on x directly. X depends on the norm of x. Okay, and so for example, in 2 dimensions, then, if these are your centers, of course this is centered at the origin, and so the effect of f is just to have the same value, right, at any radius away from the origin. And then if we take, since we're going to be using like f sub I of x, right, that's going to be f of x minus ci. And so in that case, the function f is going to have the same value, right, at all the points along some fixed radius from ci. And so you can kind of see why these are called radial basis functions, right? All right. I should say radial functions. The basis, we remember from linear algebra, means that we have a linearly independent spanning set. And so, as it turns out, these radial functions can be set up to be a basis for certain function spaces. Okay, we won't get too far into that. Now, in order for this to work, of course, the function f has to be of a certain type. And so there are some classical versions of that. So the transfer function, function's phi. All right. So the classic, and the one that MATLAB uses, is the Gaussian. And so that means that phi of, phi is actually going to take on 2 values. Phi is going to take on a value r and a parameter sigma. And so that's our width parameter, by the way. So that's going to be e to the minus, then r squared over sigma. I guess we'll say sigma squared just to keep standard. Okay, and so of course we know that that is, this is going to be centered at 0, where r is equal to 0, right? And then it's going to be our classic bell-shaped curve. And so sigma is going to define the width for us somehow. So large sigma would give us a large width, small sigma, small width. Gosh, my headphones are coming off. Okay, 2. Phi of r is a cubic function. And I've had pretty good luck with a cubic function in the past. And so that is your cubic function. The nice thing about the cubic function, it does not have an extra parameter in it, for one thing. The other thing that you might notice is that while the exponential function, the Gaussian, drops off after a certain point of time, and so we would say that the effect of this function is local. On the flip side of that, the cubic function is getting very large when you go out, right? And so its effect is not just local, it's actually a global effect. And so, of course, the problem with the cubic is that it can become unbounded on you, or at least very large or very negative. But I have not found that's a big problem, because our basis functions are our what am I trying to say? Our RBFs are centered at different places, and so you don't have to worry about the cubic function getting unbounded in a very large region, because otherwise, if it did start to become unbounded, what would happen is that your algorithm would hopefully put more centers out there, and so it wouldn't be by itself. And yeah, okay, there's some other popular ones. Actually, I don't know how popular they are anymore. They were way back when. We'll just throw down a few just because, well, it's kind of fun to see. One of them is called a thin plate spline, and that is phi of r is equal to r squared log r. That one can be problematic because of the logarithm, right? Because you can't have a 0 in there. We also have a Cauchy, which is an interesting choice, because a Cauchy function looks like what? Well, the problem, of course, is going to be that you're going to have a blow up at -1, but that's not going to be a big of an issue, right? Because r is actually from 0 to infinity. And so we're really just, when I'm drawing these graphs, I'm actually not getting the full picture. What's going on here? Let's see if I can, there we go. Okay. We're actually only getting the positive half because our domain is only in the positive numbers. So we're only getting this positive half for this one and this positive half for this one. And so this one then would be what? It's going to come down like that. Oops. Well, okay. It's not going to, so you might think, well, does it come down faster or slower than the exponential function? It comes down slower than the exponential function. And so if you want like wider space here than the exponential function, then you might choose a Cauchy transfer function instead. And there's some other ones that are in the book. I think probably the other interesting one might be the identity, because you can certainly have the identity map, and if you do that, what you end up with is kind of an interesting function. What happens in this is going to be a piecewise linear. Oh, geez. What's going on here with my pen? There we go. Piecewise linear approximation. So for example, suppose I've got data that suppose I have my centers here. This is my one data point, one data point, one data point here. And so what's going to happen is you're going to be doing something. Thank you for interrupting me, Windows. Gosh, no. Okay, sorry about that. What's going to happen, yeah, we'll try this out, but you're going to end up with a piecewise linear approximation to your function if you use the identity map for this. Okay, good. So that is the phi. So again, looking back at our RBF, what have we talked about so far? We've talked about the phi function and what that does. How to choose a phi? Well, here's a hint. MATLAB uses only the Gaussian function and nothing else. So I guess it doesn't matter that much. No, I think the cubic function is better, but that's my personal opinion. Okay. In some cases, yeah. Okay. The other thing that we haven't talked about is how to find the centers. Okay, so that's really the other key. So what's left? we have to be able to choose the centers. And then once we choose the centers, then we need to be able to solve the linear system for W and B. And so those are the two things that we'll talk about in the next video.